Hey everybody, it's Dr. D here. Welcome back. If you've been following along, we've been talking about the confidence intervals and the beginning of inferential statistics. We looked at the intuition of confidence intervals in our previous video. Today I want to give a walkthrough example using numbers, and we're going to use an intuitive method that kind of follows up on what we've been doing before. We will see that it takes a while, and rest assured that before this series of videos is over, we'll have a more efficient way to do it. But this is a useful place to start. Let me see, I have this up. Let's see, close this. I want to get a spreadsheet up just to do some calculations in a little bit. I won't need them just yet, but it'll come in handy in a little while. All right, while that's loading, we can get started. So the example we're going to look at, we want to look at the number of miles driven by renters of rental cars. Let's say we have a sample of 200 people, all driving rental cars. And then we're going to look at the mean within this sample. The average driver drove, or on average, drivers drove 325 miles. And then we are going to assume that the standard deviation of the population, standard deviation of the population, not sigma x bar, sigma x. Sigma x is 60. And what we want to know is, what is the 95% confidence interval for the population mean, for mu x, the population mean. Essentially what this says is, on average, how far did people drive? Well, we looked at 200 people and we saw 325 was the average there. But how far did all renters drive? And what can we say, given that we only have 200 renters? And this gets at something we often see from people who are sort of casual critics of statistical analysis is, well, we only asked 200 people. What can we say? Well, it depends. If we have to make one big assumption, which is to say we have to assume that these people are representative, meaning that they fall within the middle 95% of all samples. That's what that 95% is. We call that alpha, or we denote it with an alpha. It's called the confidence level. And what it says is we are going to make an assumption. We have to make some assumption about this. We are going to make the assumption, in this case alpha is 0.95, that this sample falls within the middle 95% of all samples. Now, could that assumption be false? Absolutely. In fact, we know that it will be false 5% of the time, right? So there's a 1 out of 20 chance that our confidence interval, any given confidence interval calculation at this confidence level is going to be wrong. And there's a trade-off. What we could do is we could change alpha. We could make alpha more expansive, 99%, in which case there's only a 1% chance we're wrong. But then the bounds of our confidence interval will be less restrictive, right? We'll be able to say less, right? We'll be able to restrict the possible values less. And if we set alpha to 100%, so we're never wrong, every 100% confidence interval is negative infinity to positive infinity. If you want to get tighter than that, you have to allow for some possibility that we got a weird sample. So we're going to stick with alpha equals 0.95 and work our way through. But I do want to be clear. If you think, oh man, what can we say? We only have 200 renters. Well, as long as we think that sample falls within the middle 95%, we actually can say quite a bit about millions or to tens of millions of drivers, which is to say we can say what range the average, if you were to count all of those people, would be. Which is pretty powerful. It's the reason that statistics has become so popular. That even with just 200 people and a pretty mild assumption that we can relax if we want to, we can talk about meaningfully about a larger group. We do have this assumption as well, and this one's a bigger assumption. And we're going to get rid of that next time or the time after, but by the end of the series, but not today. We generally don't think we know the sigma standard deviation of the population. We generally don't actually think we know that, but there are ways to work around that. We're just not there yet. Okay, so let's set up this problem. What is the 95% confidence interval for the population mean? To do that, we want to model this. So we're going to draw ourselves a picture. I'll make it a little bit smaller than I have the last video. And then we're going to collect our sample. And that sample, we said, had a mean of 325. That was our X bar. So our sample falls right here. It doesn't have to be in the middle, but just for aesthetic purposes, we can put it there. Now, what we want to do now is try to find the sampling distribution. We know that we can find the standard deviation of the sampling distribution. Well, first of all, we know it's going to be normal because we have a sample of size 100, right, or 200. N equals 200. Let me copy that back down here. Sigma was 60. If n is 200, that means that the distribution of x bar, which is what we're going to be trying to draw, is normal. The tricky thing, well, we do know this, right? This is going to be sigma x over the square root of n, so we can figure that out. It's 60 over the square root of 200. And I'll calculate that in a minute. We do know it, though, right? We know what sigma x bar is. The problem is, that tells us the shape. The problem is we don't know the location of the curve. And for a confidence interval, we actually only need two locations. The lowest plausible value of the curve, right? The lowest plausible curve that would yield a sample that looks like this. And then the highest plausible curve distribution that would yield a plausible sample, would plausibly yield this sample. So in one scenario, these drivers drove much more than the typical driver, in which case the typical driver would be to the left. And so we're going to try to draw that curve here. That would look like this. And our value of x bar falls at the very top end of the middle alpha, right? Alpha goes in here. Because what we're saying now is x bar could have come from anywhere in this area, but it came at the very top end of the middle 95%. So that is one extreme scenario. The other extreme scenario would be the opposite, meaning that relative to their peers, x bar was actually quite low, in which case, and the sample falls in the left end of the distribution, and this would be 0.95, and you can see now it's on the left tail. The location here, call this one mu1, this one mu2. Those are our unknowns. And now, hopefully you can see that this is just a normal distribution question. It's actually two of them kind of nested, just like any of the other ones we've done. And we have finished step one. Step one is take the question and turn it into a picture, which we've done. That's supposed to be a tree. It's a terrible tree. There's a sun. It's a picture. Anyway, we now have a normal distribution question, and we know how to do that. We use our 4 steps. Turn the question into a picture. Step 2 is relate it to the standard normal distribution. That's the z distribution. That's normal 0, 1, right? Step 3 is use p to get z, or z to get p, depending on which one we have, right? If we already have an area, we need to work to get our z. If we already have a z, we work to get our area. And then step 4 is going to be to answer the question, which in this case is going to be to find mu1 and find mu2. So those are the 4 steps we're going to take. We already finished step 1. We have a picture. Step 2 is to relate to the standard normal. Since I have 2 curves here, I'm going to do them separately. So we'll do the mu1 on the left first. Step 2 is done whenever we have the same number of things labeled, 3 out of the 4 in this one as we did in this one. So let's draw ourselves this curve. We're going to have normal distribution. It's supposed to be lined up, but it's got a mean of 0, standard deviation of 1. This is our z distribution. And then this x bar has a corresponding z right here. Call it z1. That is at the top half of the middle 95%. Right? That's what would make these two analogous, right? This is 95%. That down there is 95%. And so now we have the mean labeled, standard deviation labeled, some area labeled. We don't have the z labeled. We have one unknown, but that's the end of step 2. Well, we've got 2 of these, right? But that's the end of the first half of step 2, or step 2 for the first half of the problem. Step 3 now is going to be to use p to get z. So how do we find this z here? Well, whenever we have an area and we want to use that to find z, we can use in Excel the norm.s.inv function. And then the thing that goes in here is the area to the left. So this 95% is to the left, but it's still missing this little tail. So we have to figure out what this combined area is. Well, if we know that alpha is 95%, Then we know that the rest of these two combined, right, the two outlying tails here, this one here and this one here together they add up to 1 minus alpha, which is 0.05. Now we don't want both of them, we only want one of them, so we can do 1 minus alpha over 2, and that'll give us 0.025. And it turns out that the tail here that we want, the area to the left of z1, is going to be alpha plus 1 minus alpha over 2, or 0.95 plus 0.025. Right, that just gives us the middle 95% plus the area in this little tail is at 2.5%. So again, visually and intuitively, hopefully that makes sense. We got the middle 95% and then the 5% out on the tails, but we only need half of that. So we take one away, it's 2.5%. 95%, 2.5%, that's where the 97.5% comes, 0.975. That's our area to the left. So we're going to take this number and we're going to put it up there. Cool. And we'll use z to get p. So or p to get z. Sorry, we got that area. We're going to use that to get z. So switching back to Excel, which I opened. Let's create a new one. Okay. If we want to work on this problem, let's see. Might as well put in the values we have. We've got x bar is 325. Sigma x is 60. N is 200. Alpha is 0.95. Sigma x bar, those are all just hard-coded. Sigma x bar is sigma x divided by the square root of n. And then our area to the left, that is going to be this plus 1 minus this divided by 2, 0.975. And that should let us get our z. Our z is going to be norm.s .inv of that. And so there's our z. 1.96 essentially is our value for z1. I'll leave that there for a second in case you want to pause and read those. Okay, going back to our spreadsheet, or not our spreadsheet, our work, this z is now 1.96. And that's the end of step 3, the first half of step 3. Step 4 now is to get mu1, right? Mu1 is still the unknown. So how do we do that? Well, you'll notice that we haven't used the score formula yet. The version of the score formula we're going to be using is one we've worked with the last class, or the last problem set at least. X bar 1 minus, sorry, z1, x bar 1 minus mu1 divided by sigma x bar. Where we, the generic version of this is z equals x bar minus mu x bar divided by sigma x bar. But in this case, we've got 2 x bars and 2 z's, so I want to label them with my subscript there. And we also have 2 mu's that we're considering, so I want to label that with a subscript just to keep them separated. Now, can we use this? Well, to do so, we need 3 of these 4. We have a z, we have an x bar 1. Oh, I guess, we don't need an x bar 1. There's only 1 x bar. All right, I'm going to erase that. Sorry, if that was confusing, I apologize. We have a z, we have an x bar. We do not have a mu1. We do have a sigma x bar. So we have 3 of the 4, so we should be able to pull this off. Z is 1.96. X bar is 325 minus mu1 over, I think it was 4.24. Yeah, 4.24 is good enough. 4.24. So to find mu1, we just have to solve for mu1. All right, what we'll do first is get rid of the denominator. That's always a good first place to start if you have a fraction here. So let's multiply both sides by 4.24. I'm going to flip it around over the equal sign just for to get mu1 where I want it. But these cancel out. So on one side of the equal sign, we have 325 minus mu1. And on the other side, we have 1.96 times 4.24. All right, we got to get rid of, we want to get mu1 by itself, so we got to get rid of that 325. So we can add negative 325 to each side or subtract 325 from each side. We will get negative mu1. A little overzealous with the minus sign there. There we go. These cancel out. Equals negative 325 plus 1.96 times 4.24. And now we only have one more thing to do. We got to get rid of the negative sign because we don't want to know what the negative mean is. We want to know what the mean is. So if we multiply both sides by -1 or divide both sides by -1, Either way will work. What we'll find is that mu1 equals 325, negative 325 becomes positive 325. And then this plus becomes a minus. 325 minus 1.96 times 4.24. And we can calculate that, and we will. But first I want to show you on the drawing what that means. You'll notice I kept it together. I usually wait to the end to do my calculations anyway. But let's see. So if I move this up here, this is telling me how to get mu1. 325 minus 1.96 times 4.24. And if we look at the drawing, you can see that 325 is right here. So we're starting at x bar. And then this says move to the left. Okay, how far? Well, 1.96 is z. If you remember, z is the number of standard deviations. We've been talking about that. This is why we talk about it, so we can understand intuitively things like this. We're going to move to the left 1.96 standard deviations. 1.96. Well, that's great, but what I need to know is how many miles I am doing. So what we do is we say, well, it's 1.96 standard deviations, each of which is 4.24 miles, right? This is 4.24. So 325 down by 4.24, and then down by 96% of that. All right, let's plug these in to find mu1 back in our spreadsheet. mu1 is going to be 325 plus or minus z1 times sigma x bar. And there it is. 316.685, 316.7. And that puts us right here. So that's the lowest plausible value. So what that says is, if the true population average were 316.7, then it would be just at the outer edges of the middle 95% to get a sample that had 325 on average, right? Anything higher than, or anything lower than that, and 325 would be outside the bounds of what we had just agreed would be what we consider plausible. All right, so that's how we do the left side, and that's step 4 there. Let's look at the right side. Okay, so it's a similar setup, but now we need to do, we did step 1 already. Now we need to do step 2, and instead of being over here, I'm gonna write it down here. This is another z distribution, and it's parallel. I'm trying to make it analogous to this one. All right, so that mu2 corresponds to this z2, or I mean 0 right here, sorry, because that's the average. This x bar here now corresponds to z2, which is over here. The mean of the z distribution is always 1, and then the size of the area in between here is still 0.95. So now instead of having our z be at the top end of the middle 95%, we now have our z being at the bottom end of the middle 95%. So that's the end of step 2. We have an area known, a mean known, a standard deviation known, and a z-score unknown. That's fine. That's why we do the rest. Now we're on to step 3. Use p to get z. We did it before, and in the process, we found the size of the left tail that we happen to need right now, right? We found that this was equal to 1 minus alpha over 2, or 2.5%, right? That's the size of that tail. So we should be able to do norm.s.inv again, but instead of putting the 975 in there, we can put this in there, the 0.025. So now that'll give us z2 if we plug in 0.025 into the norm.s.inv. So let's go back to our spreadsheet. This is area to the left of z1. Now I want to do area to the left of z2. And that is going to be, sure, I'll do it. 1 minus this divided by 2. 0.025. And that gives me what I need to do my z2. Norm.s.inv of my area to the left there. Hey, what do you know? That number is familiar. Similar to some of the sampling problems we did, what we see is identical magnitude, different direction. Negative 1.96 instead of positive 1.96. That's because to be at the top end, or the bottom end of the middle 95%, you'd have to move 1.96 standard deviations, just like you would to be in the top end. It's just the opposite direction. So that negative 1.96 is my z-score down here. And sure enough, we're done with step 3. Now we have to do step 4. Very similar to what we just did, right? We've got the same setup, but now instead we've got z2 equals x bar minus mu2 over sigma x bar. and then we can just plug in the corresponding values for these. So let's see. Z2 is negative 1.96. That equals 325 minus mu2 over sigma x bar. Not sigma, well, I want the number. What am I doing? There we go, 4.24. Same exact setup as the previous one. We have to do the same algebra. The numbers are different, mostly it's just this sign, right? We have a negative z, that's the difference here. So let's see, if we multiply both sides by 4.24, that'll get rid of this denominator. Flipping over the equal sign again, 325 minus mu2 equals negative 1.96 times 4.24. We need to get rid of that 325. So we'll subtract 325 from both sides. Get negative mu2 equals negative 325 minus 1.96 times 4.24. Close it out. Multiply both sides by negative 1. These cancel. And now we get mu2 equals 325, because the negative becomes a positive, plus 1.96 times 4.24. Just the order of operations, PEMDAS stuff, and then using your algebraic methods. Okay, so this should look familiar because it's very similar to this one over here. And then if we want to bring it up top again, just like we did with the last one, we can see a similar insight. So let's try to make this small, just like the other one. You can see that if you want to get to mu2, this formula tells you what you do is you start at 325, and this time you move to the right. You move the same distance, though, 1.96 standard deviations, and that will get you to the highest plausible value of mu that would yield us this lower value of x bar. So let's figure out what that is. So that's going to be our mu2 is going to be 325 minus negative, right? Minus that times this, which is the same as plus a positive, and 333.315 is what we're getting there. Okay, great. So what we have now is two values, 316.685, 316.7, and 333.3. This is 333.3. We can put this in interval notation. We can say mu1 comma mu2 equals 316.7 comma 333.3. The question is, how far did renters drive? And we had a sample of 325 that only looked at 200 people. But what we can say is, if you were to go out and count the millions of people that drive every year, whatever, and ask them all this, and it would be very costly and time consuming, what we can tell you is, if it's true that our sample is in the middle 95% of all samples, and you know, there's a 1 in 20 chance we're wrong about that, but if it's true that what we witnessed was that, then you would expect your answer, if you collected everybody, to fall between 316.7 and 333.3. Now, if you want to be more precise than that, there are some things you can do. You can hedge your bets and say, or more precise, I guess, you can lower your standards and say, well, who needs 95% confidence? Let's be 90% confident. That would tighten it. Or you could pass legislation requiring that everybody drive the same amount. That's going to decrease that, right? Just force it on, social change. Or you could pick a bigger sample. If you picked a bigger sample, what would happen is this 4.24, which came from this right here, right? That's 60 over the square root of n. The square root of n would go up, which means this would go down if you increase your sample size. So if you want more certainty, you can ask more people. But for many purposes, just knowing it's somewhere in this region would be sufficient, right? If you need to know, okay, on average, how far are they going to drive, and you can just hedge against the possibility. Let's say you're thinking about a repair schedule. Let's assume the worst case, 333.3 would be the number you could use, something like that. Or if you want to hedge in the other direction because you're worried about revenue, you could say Well, people are only going to, gas, you're trying to charge people for gas or something. Well, they're probably only going to drive like 317. But that gives you a lot of information based on just 200 people. Certainly a lot better than negative infinity to positive infinity. Anyway, that is how you do a numerical example. The intuitive but inefficient way. If you were to do a different problem, that's what is the 95% confidence interval, what's the 99% confidence interval, every single time you would have to set it up like this, go through all these steps. It takes quite a long time. And the reason is that the intuition that's built into the score formula right here, this score formula is a z-producing machine. That's what a formula is, a machine that produces numbers, right? And this score formula right here is a z-producing machine. What we really want is a mu. Since what we care about is mu, we want a mu-producing machine. And so next time we meet, in the next video, what you'll see, I'm going to go through an example like this without numbers so that you can see how do we come up with a better method? How do we come up with a better way of finding a confidence interval that doesn't require us to go through all of this process every single time? Thank you very much for your time. If you have questions, as always, please get in touch, and I will see you guys next time. Bye.